So hello to everybody. It's 7 o'clock now. Everybody is, lots of people saying where you are. Only me, I think, has said it's been snowing, but I'm sure a lot of us have seen snow over the last 48 hours or so. Quite a few snow flurries in Reading for me. Anyway, let's start our virtual meeting, our third Southeast Area Local Centre virtual meeting. So today's speaker will be Mark McCarthy, but first you'll have to suffer me doing the intro and talk about the MetSoc, and then I'll do a little brief monthly summary of March, where in a bit of a change from from the last month, I actually have got some records to mention, so that's positively exciting. So let's start though with reminding everybody to join the Weather Club. All getting ready for relaunches, but with full access with full access to the Weather Club website, information of events and meetings about the weather, opportunities to participate in national activities, including the Great British Weather Experiment, and competitions to speak to the experts about the weather, and the new quarterly newsletter with stories and features and so on. So do that. I've just spotted D shout yay. I am the Royal MetSoc account today, so when you get a message from the Royal MetSoc account, it is from Rob Thompson. I apologise. And D, yeah, I know that area very well. So, so remember, if you're not a member of the MetSoc, you should become a member. I need to remember to turn off my phone before that keeps happening, so I'll do that while I talk along. There you go. I'm now well behaved. So if you're interested in joining in meteorology, you should definitely be joining the MetSoc. We're a historic, world-leading society and membership from all over the world of all kinds of, basically anyone interested in meteorology. And hopefully, there's lots of benefits, including the weather magazine, conference discounts and meeting discounts, and discounts on all the older journals and support grants, etc. And you can go to the MetSoc website there and find all of the fabulous information about membership. So become a member. Q&A session. So I'll include my own little weather summary in this. If you write a question in the right hand side, Simon or I are going to try and find them, and then we can answer any questions. I'll try and answer any questions, and we'll ask Mark questions after his talk. So at the end of our talks, if there's anything that's absolutely glaring as this needs now, and I like my weather summary to be, if we were in person, it would definitely be completely interactive. So ask your questions and I'll try and answer them on the fly. I've got my chat window open on the right, so please type away with your questions. And yeah, obviously be aware if we get loads and loads and loads of questions, we won't have time to answer them all, but we'll do our best. Okay. And then there's the little bit of Demio. I'm sure lots of you have used Demio by now, but if you're using Demio, we suggest using Chrome or Firefox or Safari or Edge. How many people are using a browser that isn't one of those? Probably not very many, but if you aren't, then they seem to work better with those. And then you can make your PowerPoint slides bigger with the expand button, and you can make me seem smaller. That's probably a very good idea. And the slides bigger by dragging up the middle of the bar that runs across the top. I'm doing this, of course, it's never going to be at that height because I'm always in my size. And you can look at the chat. We aren't using any polls or handouts today, so I would just use the chat. Hopefully the answer to Stephen's question is no, because Stephen is asking if anyone else is just seeing connecting with no audio or video. Can somebody tell me they can hear me and see me? Okay, good. So there's at least 3 people. So, and thank you, Simon. Much appreciated. Good. So I'm glad everyone can hear me and see me, because I think my next slide is me saying that it's the weather summary of March 2021. Okay, so let's start off with I've gone the same way round as I have been doing in the last few months, and stick with the UK as a whole, and then go smaller scale and go to Reading. So for the UK whole mean temperature of March, and mean, minimum and max were all similar sort of message. So I thought I'd just show the mean. This is where we are, about a degree above the average. But actually, of course, that's not great shakes basically compared to what we were. I note that they're still on the 1981 to 2010 averages was the default for this plot, which surprised me. We hadn't updated because my Reading averages I pull off my own website, so they are using the 1991 to 2020 averages. So there'll be a slight disagreement on those caused by that difference. But there we are. We're a little bit warm, but basically, in the grand scheme of things, that makes it about average, really. The sunshine duration, we were almost precisely on what you'd expect for March. Like, you can't actually see the pink line because the brown one is right on top of it. D, if there's still some QC needed before moving to the 91 to 2020 averages, that would make sense. And there you go. Mark says he can explain later. So excellent. Yeah. So Reading averages, hopefully QC won't be changing anything. I'm sure there will be some imperfections in there. Well, I guess what felt to me, March felt like it had been quite a dull month. And it, as I said, it's almost bang on the average. And you'll see when we come to Reading that we agreed to the UK wide, it was pretty close to average. And I think you can sort of see on my plot here on the right hand side from about really mid 2000, the mid noughties, as I shall call it, most Marches have been quite sunny. And we've only really had two below average sunshine. And so I guess I've kind of got used to it being sunnier March than I should be used to. So that's probably why it felt dull. Next, I've got the maps that I'm sure we're going to see some more of. The Met Office maps are rather lovely. And I've done the maximums in the top left, minimums in the right, and the middle is the means. And well, this is the actual temperatures, which I thought I'd show because I don't normally show the actuals. I normally jump straight into the anomalies just to show you what they look like. But really, the anomaly is what I think we normally want these maps for. And the answer was pretty widely over the UK, a little bit warmer than average for March, but not a huge amount, and less so in the south, basically. So that's the message for the temperatures in March. If we look at the rainfall, I thought I'd do the same thing and show the actual value, which, as I've laughed many times in real life meetings, is a fairly good map normally of this is where the elevation map, but it's not quite as nice as it sometimes is, and perhaps a month doesn't show it quite as well, but you can see the Lake District rather nicely. And Welsh Mountains, of course, and you can see the anomaly there. As always, I always think the anomaly maps look a bit strange, and they seem to have the odd gauge that probably is one or two gauges that seem to have been hit by a lot or missed everything. And you can see that again this month, but generally speaking, just a little bit dry over a lot, and a bit more and a little bit wet over the Lake District there, particularly. And that's really the message for the rainfall. So March has been quite average, and we'll finally see that in the sunshine. And again, Northern Ireland's been a bit dull, and the rest of us have been very average, really, over pretty much the whole of the UK. So let's get a bit more Reading centric, because as we've discussed before, I've got nice, quick, easy access to data on this and my own website to get the numbers. I've spotted a typo again. I fixed it. I fixed the typo that Simon pointed out to me, and Simon, you win because I've then promptly put it back in wrong. So well done, me. Blame the dyslexic who can't spell. So as slightly warmer on average for the maximum temperatures, but very slightly colder on average for the minimums, which made the means almost bang on average for March for our 91 to 2020 averages. Rainfall was a little bit dry at exactly 30 millimeters and 110.9 hours of sunshine is just 7% down on average. So although it felt to me like it had been a pretty dull March, it was pretty average really. But I did promise you I'd got a record, and for once we had the 30th, so almost the very end of March, we had the highest Tmax since 1965 recorded. And so that's a pretty good record really, I think. And it was also the driest March since 2015, which, based on what I'd said about the winter last time, was a pretty good record. Last time I really struggled to come up with anything at all. So March was, but really, as a whole, the month was no great shakes, basically. And then I thought I'd point out a big record because Simon would be very upset if I didn't point this out. Yesterday in Reading, we had a dew point at minus 13.6 degrees C recorded, which was a low in sort of almost 30 years. And at the time, air temperature was 6.8, which made it 19%. I was disappointed. I'd not actually tried to do the washing, because at 6.8, I wouldn't normally think this is a great day to hang the washing out, but it probably would have been perfect. And I didn't do it. So that's a shame. I see Stephen's still struggling and has apparently tried. Stephen, my suggestion is if you've got one, try a different browser. Hopefully you can get in, because it seems like everyone else can. He probably can't hear me saying that though. Okay, right. So I've got finally my last section on the summary. I searched around for some interesting quotes on March, and I've managed to find one from tonight's speaker, which was positively exciting. So Mark McCarthy from the Met Office's National Climate Information Centre about March said, with the exception of some record-breaking highs at the end of the month, March didn't deviate too much from what we'd expect to see for the time of year. The most notable factor was the high temperatures at the end of the month, with a number of stations recording their warmest March day since we've been recording the data. Not quite in Reading, but we were pretty close. And this sort of area, it happened in quite a few places. So that was March. Didn't see any more questions. Let's go. That will leave me to introduce Mark. I'm going to quickly jump back to the very beginning slide, just so I have the virtual meeting, How Much Rain, and to introduce you to Mark. So Mark McCarthy is the Science Manager of the Met Office National Climate Information Centre, the NCIC, providing monitoring and analysis of UK climate variability and change by providing the underpinning observational data and analysis of the UK climate. Mark joined the Met Office Hadley Centre in 1999, which is the same year I joined the University of Reading. So obviously a cool year for joining where you are. And he spent the first 7 years of his career working in climate monitoring and attribution teams, studying observational records of variability and change in atmospheric water vapour, while he also completed his PhD at Imperial College London on the same topic. He then moved to the Climate Impacts Group to research urban climate impacts, specifically understanding how regional and global climate change are expressed through the urban heat island. He's been actively involved in a wide range of projects from the Amazon to the Indian monsoon, utilising developments in the land surface scheme within regional and global climate models. And he returned to climate monitoring and attribution team in October 2012. And on that note, I shall move you over to Mark's presentation slides, and hopefully these will come up, and pass you to Mark.
Hello, good evening everyone. Hopefully you can all hear and see me fine. Thank you for the introduction, Rob, and thank you all for the invitation to speak this evening. So everything I'm discussing this evening, though, is very much team effort. So I would like to acknowledge my team and other colleagues that have really led or contributed to much of what I'm going to say this evening. So I've sort of included their names on this first slide here. To set expectations, so how much rain, ? I'm going to present the rainfall event of 3rd of October 2020, so hopefully still reasonably fresh in people's memories. and particularly the climate metric of a UK-wide daily rainfall. Putting this into the context of how that particular statistic is arrived at and how robust it is, and then conclude with some recently published results from a climate attribution study placing the record of 3rd of October into a present and future climate context. So 3rd of October last year was provisionally the wettest day on record for UK-wide average rainfall of 31.7 millimetres. And really, as the sort of headlines demonstrate here, communicating some of what we do and our science to the general public in a way they find interesting and engaging can be challenging. And this event was widely reported in the media as enough rain to fill Loch Ness. A catchy headline, but in this talk I'll use this event to dig a little bit further into the origins of that number, that 31.7 millimetres, how we derive that, and how it supports the sort of the wider set of climate series we use, we maintain at the Met Office and we use for monitoring climate change here in the UK. But I'll start at Loch Ness. At a little over 55 square kilometre area and a mean depth of around 130 metres. It's the UK's largest lake by volume. And this link to the rainfall event certainly captured interest. But I'll confess, personally, I still can't really visualise the volume of Loch Ness beyond it being sort of a lot of water. So the same team discussion which this particular fact arose, we sort of played around with several options of how much water is it, how much rain was there in that particular event. So another option was the spherical raindrop. So if all of that water was a single sphere, that would have a diameter of around 2.4 kilometres. Or as a unit of time, a single sort of typical kitchen tap would take about 2.4 million years to fill the loch. In any event, we stuck with the Loch Ness statistic, and it seemed to cause a reasonable amount of reach and engagement with the communication of this particular event. So where this number originates, I mean, for the area of the UK, so just over 242,000 square kilometres, a rainfall depth of a little over 30 millimetres averaged across the country would be sufficient to fill the loch. As an aside, it would be close to about 1 millimetre for a country the size of Australia. So the map on the right shows the rainfall amounts from the 3rd of October 2020. So here the darkest blues being associated with areas in excess of 30 or 50 millimetres, extending widely from southern England to northern Scotland. Parts of eastern England and the far southwest did escape the higher rainfall totals that day. But it's really quite unusual and notable how widespread. So for an individual location, not necessarily extreme, but the widespread nature of this rainfall really was. It was also moderate and persistent. So generally the rainfall rates mostly less than sort of 4 to 5 millimetres per hour. And the fronts associated with the event didn't contain significant embedded convection. So this, coupled with the fact that the preceding September, the antecedent conditions were relatively dry, actually the impacts from this event were relatively limited. A sort of reminder that rainfall severity of an event does not always relate directly to the hydrological or social impacts from that event. But from this map of the UK, if we average the rainfall amounts across the whole of the country, this gives us the 31.7 millimetres. This is satellite image from the 2nd of October 2020. This is showing Storm Alex, which was named by Meteo France. And for much of the country at that time, it marked the transition to more unsettled autumnal conditions over the UK. This visible satellite image showing the centre of Storm Alex sitting just to the southwest of the UK, with somewhat clearer conditions over northern areas that day. And here is the associated analysis chart. Well, this is from 1800 on the 2nd of October. Very strong winds across the southern half of the country. Hurricane Force 12 warning was issued for the Biscay area on the 1st, and heavy rainfall fell quite widely across southern England, and there was an amber warning for rain also issued, associated with the tracking of Storm Alex. But after Alex had departed the UK, it actually tracked southeast into the continent, where it resulted in some really extreme rainfall, in excess of 500 millimeters in some of the worst affected areas in southeast France. For some regions, about 3 months worth of rain in a few days, leading to some severe flooding to parts of southeast France and northwest Italy. Dozens of homes destroyed, roads washed away, and several fatalities. But at this time, on the 3rd and 4th of October, if we look across the UK, fronts actually were associated with a new area of low pressure, and it's those that brought this prolonged and widespread heavy rainfall to the UK. I mean, as with all such scenarios, I've no doubt there'd be enough to fill several hours of discussion, sort of unpacking everything in this analysis chart alone. But for the purposes of this evening, I'm going to consider just the rainfall captured within the UK network of rain gauges that day, and for the standard rainfall day from 0900 to 0900 as 24-hour rainfall amounts. Okay, so as I mentioned, heavy frontal rainfall affected large swathes of the country through the 3rd and 4th. Again, showing the map here for, on the left, the 2nd of October, as the passage of Storm Alex across southern England, and then the associated frontal rainfall on the 3rd of October. So parts of central southern England, the Thames Estuary, and parts of eastern Scotland all recorded more than their normal October rainfall just in the first 4 days of the month. And for most of the country, October is climatologically the wettest month of the year. And really, the marked feature of this 3rd of October, I'll stress again, is how widespread these higher rainfall totals were. A number of notable extremes recorded that day, with rainfall around 50 to 60 millimetre mark, including Oxford, London, Preston in Lancashire, Balmoral. The map on the right shows all stations that recorded their October daily rainfall record. The colour indicates the length of the station record. So the yellow circles are stations that have at least 30 years of observations, orange 50 years, and red more than 75 years. For Oxford, 60 millimetres that day made it the 6th wettest day in what is nearly 200-year series for the site at Oxford, so the longest available observational series available in the UK. We can also look at this one day in the context of the year overall. 2020 was the 6th wettest year in a series from 1862 for the UK. This chart shows the UK-wide daily rainfall, so all 365 days for the year, or 66 days for the year. I've highlighted the peaks associated with storms Ciara and Dennis in February, the 3rd of October event, and also Storm Bella on the 26th of December. The other notable factor you can see here is also the marked transition from the exceptionally wet weather in February last year into the exceptionally dry spring that followed. We have developed a daily UK rainfall series from 1891, which I'll describe in a little while. So that amounts to over 47,000 days. In this record, there are only 40 days where the UK-wide area value exceeds 20 millimetres. So that's less than 0.1% of all days. 3 of those days have occurred in 2020. Storm Dennis is the 3rd highest such value on record, and Storm Ciara is the 31st highest. Storm Bella at the end of the year is I guess a notable near miss. It was just marginally below 20 millimetres, but notable in terms of, again, widespread high rainfall amounts for the UK. So 2020 really did contain numerous notable extremes through the course of the year, but these one-day rainfall events, 3rd October, Storm Dennis and Ciara, are particularly notable in that context. It's also notable of these 40 days where we get a UK value in excess of 20 millimetres. They do very much preferentially occur during October. So of those 40 days, 15 of them have occurred in October, and as we might expect, many of the others through the autumn and winter season. So October, clearly a month well suited to supporting the sort of widespread frontal rainfall events that would be associated with these higher values across the UK. Also worth mentioning that for February there are 4 such days in the historical series, and 2 of those are from February 2020. Looking at it in a longer historical context, what I'm showing now is a time series. So this is the highest UK daily rainfall amount by year. So basically it's taking the highest daily value for each year back to 1891. So thanks to 3rd of October, 2020 tops this series by, for now, a reasonable margin. I'll come back to that in a moment as well. And is provisionally the wettest such day. 25th of August 1986 is the second event in that ranking. So that was associated with the remnants of Hurricane Charlie at the time, and rather unfortunately coincided with the bank holiday weekend. And Storm Dennis in 2020 comes in 3rd in the 130-year series. However, so there are several things that are interesting about this particular series. The notable extremes are one. But prior to around 1930, there is a relative absence of notably high values. So the long-term trends in this series are somewhat sensitive to the choice of start and end point of the series. So this is something of a note of caution at this point. I'll come back to it again in the talk. But whether this is a real feature of climate and our climate of the last 100 years, or is this potentially an artifact of the observational series and the sampling and the data that we have available to us, particularly in this earliest era in the sort of late 19th and early 20th century. So I'll come back to that point in a little while. But all of this are reported in a paper now online by my colleague Mike Kendon and myself, published in Weather. Here we directly compare the rainfall amounts for these 3 days from left to right. The 3rd of October 2020 that we've already seen, 25th of August 1986, and the 15th of February 2020. We can see from this that the 1986 event in the middle was largely confined to England and Wales. So that does actually remain England's wettest day on record by a reasonably safe margin. And Scotland was largely quite dry that day. So the other 2 events were more widespread across the whole of the country. The highest totals from Storm Dennis were which is the February 2020. So they were largely, but not exclusively, over the upland areas. So something we may sort of more typically expect to see, as Rob mentioned in his slides as well. Whereas in contrast, the 3rd of October 2020, it was very much through central England and eastern areas of Scotland that recorded the highest accumulations that day. Okay, so I'll just take a breather slide and change tack a little bit. And I'm going to talk more about the origins of this data set for a sort of UK daily rainfall values and where this 31.7 millimetre value comes from, and what caution we might want to attach to the provisional nature of that. In any historical climatology talk, particularly on rainfall, though, I've always got to give a hat tip to George Simmons, who in 1860s single-handedly transformed and systematized how we record and study rainfall through the establishment of the British Rainfall Organisation. So from rallying a network of a few hundred amateur observers across the country in 1860, he had a network of over 3,000 rain gauges by 1900. So we are still very much indebted to and rely heavily on much of the data that Simmons collected and the work that he did. The full British rainfall collection have been scanned and they are, available through the Met Office digital library. And his reporting cards and a lot of the data are also held in the National Meteorological Archives. So we continue to undertake digitisation of some of the historical data that he's collecting, that he collected, and use it to add considerable value to our climatological records. And clearly mapping of the rainfall data is nothing new either, and that's not something we have invented recently. And I had a nice animation that overlaid these, but we will have to make do today for a side-by-side comparison. But it is still encouraging that we can quite faithfully reproduce results that were first published over 100 years ago. Here we compare the map of a particular heavy rainfall event affecting parts of Norwich and Norfolk on the 26th of August 1912. This is comparing the map originally published in the British Rainfall publication of that year on the left in the grayscale, and that's compared with the our contemporary analysis on the right, the legend that has been scaled to match the contours of the original British rainfall map. So that's a good news story. That's quite nice. The black dots on the right-hand map show the locations of the rain gauges that we have with digitized daily rainfall available for 1912 currently. Yeah, that looks like a very good news story, but there's a sort of useful point to make here, is that at the large sort of national regional scale, we can see these two maps are in very good agreement about what was going on that day in terms of the rainfall and its distribution. However, if we kind of zoom in to smaller, finer scales, that's where we do start to see differences. So there'll be differences in exactly where the contour boundaries lie or the extent of the heaviest rainfall. So that's a sort of note of caution for one of the strengths and weaknesses. One of the key motivations for the production of these data sets is for looking at that national regional scale picture, but we have to accept that there are limits in how finely we can map these data, particularly in the earlier era where we do not yet have all of the data fully digitized. Okay, so our current UK national gridded climate data set is called HAD UK Grid, and it's built from our collection of in situ observations. We interpolate the observations to a uniform 1 kilometre by 1 kilometre grid, providing complete coverage of UK land areas, plus the Isle of Man. The data has monthly rainfall from 1862, temperatures from 1884, daily rainfall from 1891, monthly sunshine from 1919, and other variables from 1961. We share the data under an open government license, so it's free to use for any application. It is built from over 100 million observations in total, producing over 100,000 individual grids. And the paper by Dan Hollis, published in the RMET's Geoscience Data Journal in 2019, documents in more detail the process and methods, which I'm going to summarize here. The heart of the operation is essentially the process of converting a set of irregularly distributed station observations, whether that be temperature, rainfall, wind speed, humidity, to a uniformly distributed set of points. So here I'm showing a sort of a schematic example on the right. So on this map, the green crosses may represent stations that we have, and the pink dots are the grid points. The evenly distributed grid points that we wish to estimate values for. The grey shading represents some topographic feature. So in this case, maybe the elevation, with darker shadings representing higher locations. So perhaps the green crosses are temperature values, and we're trying to determine the temperature at the top of a hill where there is no station, for example. So we need an interpolation scheme that can use the available observations, but is also able to interpolate outside the range of the observations that it's received. So in order to do that, the first thing we want to do is, before we interpolate the data, is determine how much of the spatial field we're trying to represent can be predicted from other factors. So that's from the climatology or from other topographic features or topographic factors that we know. So the first thing we do is convert the observations to anomalies by removing the 1961 to 1990 long-term average, because that's our sort of stable reference. From these anomalies, we then conduct a multiple regression analysis against a range of potential predictors. Now, the exact makeup of these predictors and what's used varies by variable, and some considerable work was done by colleagues Matt Perry, Dan Hollis and others a number of years ago, looking at the appropriate models to use in this context. But there'll be a mix of things like the elevation, terrain shape, the latitude, longitude, the urban fraction, and the proximity to coast. So factors known to affect climatological parameters. In this context, because we're talking about daily rainfall, the daily rainfall grids themselves don't actually use the regression process, but I'm sort of describing them here for completeness. So after we've done these transformations on the data, we're left with a set of residuals that we feel can't be explained from known climatological or topographic effects. So the expectation are that these residuals have a larger spatial scale and higher sort of correlation with each other than the raw observations alone might do. So these residuals are then interpolated using, in our case, an inverse distance weighted approach, so that the weighting of any individual observation scales with the distance from the point you're trying to interpolate to. And we also include further functions to account for clustering of stations. So if we had sort of a cluster of rain gauges to the west of a location and an isolated station to the east, it would sort of preferentially boost the weighting so that you got a better geographical coverage. Finally, the interpolated residuals then get recombined with the topographic fields and long-term averages to produce the gridded product and the various map products that we provide. The process, I'll just quickly touch on for producing the grids. I mean, it includes what we refer to as a sort of an upstream process to collate the station data from our station climate archive, conduct quality control to filter out non-standard sites or problem areas. We also have an automated curvature test because of the volume of observations we're handling and the volume of grids that we're producing. This is all now, in the past we used to conduct a manual sort of visual inspection checks, but now we have an automated curvature test to look for areas with sharp gradients in the field of curvature that may be associated with sort of bullseyes like a stuck rain gauge or features, undesirable features for producing smooth spatial fields. And as the question was raised earlier about 1991 to 2020 averages, actually our full data acquisition and quality control process continues for several months beyond. So actually the quality control process for all of the observations for 2020 is still ongoing at the moment. So we have not yet transitioned to 1991 to 2020 averages and plan to do so later this year. New versions of the data set get evaluated once they're produced, evaluated against the existing versions and downstream products, so the aerial statistics, maps, charts, graphs, etc. Can be derived from them. So this is now a largely automated process, and we're just working on making the software, the code, which is all in Python, available through GitHub, for those familiar with it, as a repository. So the intention is that we can make the methods and the software that you're using also publicly available for the transparency of the science and the data processing that have gone into producing these climate monitoring products. The map on the right here is simply an example from an early 20th January 1891, so in the first within one of the daily grids from the first month of the daily rainfall grids. And again, the black dots give an indication of the station coverage that we have for that time. So this account of the rainfall data we have available from which to produce the gridded data products. So we have years running along the x-axis and we have number of stations running along the y-axis. There's a cliff edge in 1960 which reflects the limits of data that have to date been digitized. So thousands of rain gauges were operating throughout the 20th century, but not all of the data have yet been digitized and made available for products such as our gridded climate data. So currently, from a peak of around 5,500 rain gauges in the 1970s, the current network is just under 2,500 rain gauges in present day. However, the majority of these are not reporting in real time. So the full, as I say, the full data collection and QC process takes a few months. And working with partner agency, the Environment Agency, SEPA, NRW, Northern Ireland, who also manage very large rain gauge networks. So our provisional rainfall data are therefore based on around 1,000 rain gauges. So our current estimate of 31.7 millimetres for the 3rd of October 2020 is based on 1,000 rain gauges. And when we come to revise that value in a few months' time, that will be based on more than double the number of rain gauges. So we typically reprocess the data in late May, early June to update the preceding year's data. The early indications actually from the additional SEPA data for Scotland that we've received do suggest that actually the 31.7 might drop a little bit by reducing the rainfall amounts across Scotland a tad. But we won't release that until we've sort of completed the full analysis. So clearly the quality of the grids that result from this approach is dependent on the quality of the data going into it, and it's going to be impacted by essentially the order of magnitude change in the availability of data available through time. So here, I'm just showing an example of the point uncertainty estimated as the root mean square error from a leave one out approach. So basically where we withhold a station at a time from the gridding and sort of estimate that station's value from the interpolation process. So for the full network, so we're going from sort of the densest network on the left of this histogram to a network sort of close to the distribution we have in the 1890s on the right hand side. So the RMSE is about 1.5 millimeters for the full network, increasing to close to 2.5 millimeters for the 1890s network. And some further work on this was published by my colleague Ian Simpson and myself in a paper a couple of years ago, comparing a number of available rainfall data sets. So we produce one, the Centre for Ecology and Hydrology also produce a gridded rainfall data set for the UK called GEAR. Again, that's also freely available to use. So actually, for us, it is quite valuable to have these multiple data sets so we can explore some of this structural uncertainty that results from the choices and the decisions that we've made in our methodology. So in this paper, we ran some experiments reproducing some contemporary modern day rainfall extremes using severely restricted numbers of rain gauges. So in this case, again, around 100, just over 100 rain gauges. So the maps on the left are showing the distribution of the full rain gauge network and a diminished network of around 100, which approximates to the sort of distribution we have in the 1890s. And the difference resulting from those is shown for two particular examples with very high UK rainfall totals, the 29th of October 2000 and the 25th of August 1986. So here again, the bias at the national scale in this national, the UK daily mean value is relatively small, and it's less than 1 millimeter. But the maps on the right do show that local differences can be larger, significantly larger. So at a particular point, maybe in excess of 60 millimeters in some cases. So this is, again, a sort of reminder that one of the primary purposes of gridding to this resolution is so that we can produce consistent statistics for complex geographies, say river basins or countries or counties. But for the earlier data, there will inevitably be uncertainties in the detail at very localized scales. So the extent of the heaviest rainfall, that sort of thing. And a sparse network is just not going to be able to pick up all of the fine structures of the rainfall of a given day. So the interpolation, we're giving it some additional topographic information, but we're not giving it additional meteorological information for the day in question. And this can be a particular problem for things like summer convective situations, for example. So this is just one of those sort of limitations of, particularly when we're looking at something like daily rainfall from these type of data sets. However, for UK daily rainfall, which we've been discussing in this talk, if we compare the estimates from our provisional 1000 gauge network with the full network, so this final minus provisional in this case, for this example, for all days for the year 2019, the differences are again generally very small, less than 1 millimeter, usually no more than a few tenths of a millimeter, including for the heavier rain days in that. So the statistic itself, the UK daily rainfall, is pretty robust, and so the provisional nature of that report and that value certainly doesn't undermine it, or the conclusions that we're drawing from it. The data set itself is, we have adopted a process to allow for continual and incremental improvement to this data set. So we're recognizing that we have an ongoing and continuous process for the recovery of historical data, and a continual process for improving the quality of some of the earlier data that may not have been through as rigorous quality control as our modern observations do. So here we have an example from, again, just another day from the series, a particularly wet day, 27th of October 1903, comparing the first version of our data set, which contained at that time 120 rainfall gauges, then through data recovery activities at the Met Office, and from actually the brilliantly successful weather rescue project led by Ed Hawkins of Reading University that digitized a lot of early daily weather reports. This has increased significantly through the last two versions, so we're now sat at over 170 stations for this particular day. And again, we're sort of seeing that the impact this is having is changing some local areas and regions as we improve the detail in some previously data sparse areas, but it's not changing the big picture. I'll just mention version control briefly because it's something we do get asked about. We update the data sets in June each year, so there's an annual update process. There can be a bit of a delay getting it up onto CEDA, where it's available for public download and use. The versioning numbering system, though, to help users follows a major, minor, incremental model of version numbering, just to help users determine the significance of the changes that we've made. We do also provide a comprehensive change log for each annual update as well, because we are aware that not all users appreciate change, particularly in the historical data. But this is why the historical numbers can also change from year to year. And because the interpolation process and the gridding process can feed data through the regression model and uses other models, so all values and all numbers can change a small amount as we increment the version, and we may introduce additional data into the data set. So the first release we made of this data set was back in 2018. Since that time, we have we add each year's additional data, and for the last couple of years have also been adding additional recovered data from past years, particularly the late 19th century and early 20th century have been a particular focus for improving in recent times. Okay, so coming back to our time series of the annual maximum daily rainfall for the UK, we can see that given the previous discussions about the sampling uncertainties and the sort of expected size of those, the climate and meteorological factors exhibited in the variability in this series are significantly larger than that sampling uncertainty that we have at the UK scale. So this is potentially a useful metric for monitoring our climate. Although I will just retain that I think we do still have a little bit more analysis and some scrutiny, particularly on the early 19th, the earliest data from the late 19th, early 20th century. And that will benefit the most from continuing and further digitization of more daily rainfall data from that era. Okay, so the third part of my talk, I'll conclude with a brief discussion of some recent results from an analysis conducted by my colleague Nikos Christidis, Daniel Cotterill, Peter Stott and myself, putting this 3rd of October rainfall event into context in the context of this UK daily rainfall statistic. There is mounting evidence from a growing number of attribution studies that rainfall extremes in the UK are becoming more likely due to the influence of human-induced climate change. The attribution methods developed by Nikos and others have therefore been applied to the context of our 3rd of October rainfall event as a sort of an interesting extreme from 2020. Which actually became a study that's the first of its kind in this particular regard. So for the analysis, 9 climate models contributing to the World Coupled Model Intercomparison Project Phase 6, or CMIP6 for shorthand, were used that provided a total of 32 simulations using all forcings, so natural and human-induced human forcings on climate for a scenario from 1850 to 2100 using a medium emissions future scenario. This was contrasted to an ensemble of 41 simulations that use natural-only forcings, and a further 5,000 years of control simulations for estimating the natural variability. What this chart is summarising is the smoothed ensemble average of the maximum UK daily rainfall. Reflected, so this is reflecting the sort of shared forced change in this particular metric across the all forcings ensemble. So it doesn't exhibit large year-to-year variability because that's been averaged out in this example. And what we can see from this is that the climate models are suggesting here that there's very little change actually up to the end of the 20th century, and then following a relatively smooth increase from that time onwards. This figure taken from the paper published in Atmospheric Science Letters is the plot on the left is essentially the same data, but a different. The yellow line is the same as the line presented in the previous plot, but now the red and the green show all the values from all of the model ensembles that were available for the all and natural forcings as well, along with the observed values for the 1986 and 2020, which have been included as the reference points for the attribution study. An interesting point to note is also in the figure on the right is showing the variation and the change in the variability in the annual maximum daily rainfall, which is referred to as RX01 in the study, which is what that reference refers to. So the study also found that the variability of this metric also increased in the all forcing scenarios relative to the natural only scenario. The trends in the variability have been compared and evaluated quite closely between the observations and the model to evaluate the performance of the model in simulating this particular metric. A couple of figures here, again, taken directly from the paper. The upper panel is showing trends from different starting points in the observational series as the black curve, and in the spread of the model ensembles in the red shaded area, and from the model mean for the red bar. And the grey bar just shows the 0 line. So if we take a simple trend estimate from the start of the observational series in 1891, we have a positive trend that actually sits outside the range of those simulated by the model ensemble. We did look at equivalent statistics from reanalyses as well. They also show some discrepancies with the observations for these earliest years. So again, so this is just reiterating that some further scrutiny is required on some of this early data, and that's an area that will be really interesting to explore a bit further. The lower panel is showing the observed histogram in grey shading of basically the variability, detrended variability in the observations with the model distribution, showing very good agreement in the variability in this particular metric. So that's a promising result from the model evaluation. Using the large ensemble of the natural forcings and adopting a new method to essentially use the very long control simulation run to perturb that with the all forcings run to create large data samples from which to conduct more robust extreme value analysis for these sorts of extremes was undertaken to estimate return times for rainfall events comparable or worse than the 3rd of October for UK rainfall. So having done this in the natural climate scenario, this comes out with an estimate of a return period, a central estimate for the return period of around 322 years return period. For the current climate, so accounting for human-induced climate change up to this point, that reduces to a return period of about 1 in just over 100 years. And under a medium emission scenario, by the end of the 21st century, that comes down to 1 in 33 years. So while in all of those scenarios, this remains an extreme rainfall event, there is evidence that human-induced climate change is having an impact on the risk of these events occurring, or the likelihood of these events occurring. So to summarize, well, 3 simple bullets to summarize. UK daily rainfall provides a robust climate metric for monitoring particular types of widespread rainfall extremes for the UK. 3rd of October is provisionally the wettest such day in a series going back to 1891. And climate change has made events as similar or wetter than 3rd of October 2020, almost 3 times more likely, just a little bit less than 3 times more likely. Mention a couple of next steps in terms of the provisional data. A recent success is we're now receiving the real-time data from the automated gauge network from SEPA. So comparing our provisional data from the 22nd of March this year with the 23rd of March this year, we've added around 180 additional stations to Scotland for the provisional estimates. So that's a good news story. And for the next version of HAD UK Grid, we're working with Ed Hawkins from Reading University, whose incredibly successful rainfall rescue project, which ran during lockdown number 1, had produced over 5 million additional monthly rainfall observations for the period before 1960, which we can incorporate into the next version of HAD UK Grid. So again, a very positive impact from ongoing data recovery projects that are really valuable for datasets such as this. And they will have a real impact on the quality of the gridded rainfall data. So this is some earlier work where I was comparing the potential impact of including the rainfall rescue data into the data set. So the y-axis here is showing the estimated grid errors grid error amounts in the gridded data set. The x-axis is showing year. The blue curve is the estimated uncertainty in the current HAD UK Grid product, and the orange is what we estimate the impact will be of including the additional rainfall rescue data. So that's, again, a positive news story. So I will conclude there. Thank you very much for your attention, and I'm happy to take questions. Thank you.
Moment, so we can sort of go through the I'll scroll back to the beginning of the questions, as I got quite a few. And typically I can't accept my own questions into the question checking thing. So let's just scroll back a bit. Well, there was quite a few that were all quite related, so I'm going to pick this one initially, partly because it was partly related to my question as well. It starts with that's an interesting point, but we'll ignore that bit. And so in future, is there any plans to integrate radar data into the HAD UK rainfall records? I'll let you answer that question, and then I'll ask the question I had that was quite related.
At the moment, there is no immediate plan to do so, but it is something we have recognised as it's on the list of would be good to do at some point. So there has been work done by colleagues in observations. Ciara and Dennis in particular has done a lot of work on the blending of rain gauge and radar climate products. One of the particular values for HAD UK Grid is the historical series. So we want to have something that is as consistent as we can make it back into the 19th century. So clearly our data set precedes radar by quite a number of years. So the question mark for us about that is the value better to incorporate radar data into the HAD UK Grid product, or is it a better value to have an independent or a separate radar gauge product that covers the period available from the radar era?
Okay, so I'll go for my related question next, which was, so I'd asked in the chat, but I can't mark my own question, so I can't make it come up. But my question was, how representative, when it came up when you were sort of showing how you go from gauge values to the grid, how representative is a rain gauge's rainfall total, and I guess really daily, compared to its surrounding area? So, I mean, my feeling is a rain gauge is the amount of water that falls into that kind of area. How well does that map onto a grid where we're talking hundreds of meters, if not kilometers?
Yeah, that is a very valid point, in that they certainly rain gauges located within the same station enclosure can record different values, and certainly there are some notable some of our notable climate sites in the UK have multiple kit. Oxford is one example, Sheffield is another, where there's a Met Office rain gauge, and there's also separate rain gauges available, and they will differ day to day. So yes, that is a valid point. The representativity is difficult to capture, but so that's why we do this work, trying to evaluate the impact of the sampling on the products that we're producing. So where that's particularly going to come into its own is that there will inevitably be uncertainty in, say, where you have a portion of the country that is dry and a proportion of the country that is wet. Exactly where that dividing line is going to end up is going to be sensitive. But ultimately, that is why we have, for rainfall, we have a national network through collaboration with the devolved environment agencies. We have a network of several thousand rain gauges, whereas for other climate parameters, we have, so our climate network is around 400 stations. But for rainfall, we recognise we need thousands.
Yeah, that's brilliant. So I'm going to go for the next one, which was sort of along the rain gauges line again. So let's push the answer live button. So how do the automatic rain gauge readings used at this AWS sites and other sort of sites, lots of automatic sites now, compare with the manual rain gauges read by an observer? And there's a similar question that is further up about different types of rain gauges that, while you're answering, I'll bring that one up and come back, because I think it's similar. So these days we've got more and more, not just tipping buckets as an automatic, but weighing gauges and so on. How well do they all compare with each other, and is it something you have to factor in?
The observations team in the Met Office do a lot of work on the evaluation of the kit and the calibration of the kit that goes out, so that the equipment is as consistent as it can be. Invariably, yes, there will be differences in different rain gauges and different rain gauge designs. For the purposes of our climate products, we use both the automatic and the manual rain gauges. We don't treat them any differently as it stands, and we haven't got any strong evidence that they're causing a problem in that particular regard.
Okay, yeah, good. Unless, what's my next question? I'm going to go for. So you commented that the number of stations is declining. It's certainly something I've noticed looking at rainfall over the years. And Dee asked the question, why is the number of stations declining? There were a couple of questions that sort of followed on from this one. So I'll just click finish answering that one, and I'll move on to the next one, which was where actually Jonathan suggested, could it be an increased reliance on radar for the more day-to-day uses of the rainfall measurement? And it's an excellent question. Why are we seeing less gauges and stations generally? And I fear I know the answer that you're going to give me.
Yeah, it's a trend that's seen worldwide, actually, that the number of observing stations has declined. I mean, as a logistical challenge, it is very labour intensive to manage and maintain these networks. However, the decline in recent decades for many applications are compensated by the increased availability of remote sensing. So it's radar, but there's also increased availability of satellite observations and other sources of observations that are available.
The next one I'm going for is one I probably should have spotted earlier, because it would have fit in better with some of the other questions. But Anthony asked this one. So how do you check the effect of exposure in hilly areas? I'm guessing hilly stations, I guess this is, which, I mean, particularly on a windy day, could be really problematic. From my own, I know that on a really windy day, gauge data isn't as reliable. How do you handle that kind of problem?
Yeah, again, so that's not something we actively adjust for in the data that we're using. I know some other Met services do make adjustments for the wind effect. The exposure, the site exposure is managed, and sites will introduce interventions such as turf walls around enclosures, so to try and reduce overexposure, particularly for isolated locations. So I don't know if that sort of answers the question. We're not actively making adjustments or accounts for that effect within this data set, but we're doing that consistently throughout the 130 years, if that makes sense.
Yeah. Well, I'm going to move on to a sort of different topic of questions now, and there were a few sort of about our particular case of the 3rd of October and our wettest day, etc. So let's go for the first one we had, which was your very first question that came up in the chat at all. So John Charlesworth said, did the upper air pattern, which suggests such massive totals as we had on this day, did we have a jet stream that was unusually strong and well-defined sort of entrance, exit, etc.? Was there an upper air pattern that helped? I mean, I'm sure everything helps to get the most extreme, but was it upper air playing a role here?
Not that I'm aware that was a primary factor in this particular event. No, but I'm happy to be debated on the some of the meteorological detail of it. As I sort of mentioned up front, there's quite a lot to unpack in the analysis of what was going on that day, intertwined with Storm Alex over the continent and another low pressure system to the north of the UK. So these sorts of scenarios tend to be associated with these sort of frontal systems that just persist. It's that persistence of rain over a long duration of time that is particular, and the orientation of the fronts on that day really did sort of track from northern Scotland down to central southern England.
Right, so the next one is sort of a double question again from Andrew that was sort of about our case. So first one is, what was the actual period of rain that resulted in the average amount of 31.7? And because of the way the system works, I can click on that one. And from which direction did the rain spread across the country? So this is more of a meteorologically what was going on that created that.
Yeah. So, so the first question, the period of time we work with a climatological rain day. So the 3rd of October rain will be the rain that fell between 0900 on the 3rd of October and 0900 on the 4th of October. So that's the first question. And actually the rainfall just kind of fell everywhere for most of the day rather than passing through. So you can sort of see on the 3rd of on the rainfall map that the regions, parts of East Anglia, Lincolnshire, and the far southwest of England sort of escaped a lot of the rainfall that day. But then equally so did, so there was a lot more rainfall across eastern Scotland than across western Scotland and the upland regions.
Yeah. Right. So the next question is one that I think an excellent question from Chris, and I'm going to sort of include a D question that was from earlier on that I'll tag in a similar sense, really. So this first one is, we've commented, and you've commented that we've got the decrease in observing stations and so on. Do you think in future we'll be able to use the sort of amateur stations of WOW, etc.? We know they're not perfect, but we also know quality control on them can make them really, really useful. Do you think there's ways to fill in the gaps, etc., to make the gridding type products well? And I guess in a similarly related note, do you think like digitization of things like the Rainfall Rescue of Ed Hawkins, are they such digitization efforts still ongoing?
So is that two questions? So yeah,
It's sort of two questions. As far as I'll tag up these to make sure it lists itself as answered while you're talking. But I guess they're kind of basically, we can go both backwards and forwards with amateurs helping with the digitization, and Rainfall Rescue is fantastic. And I can say my own mum, I managed to convince her to do several hundred of those, just sat while she was bored in the first lockdown. So well done, my mum. But are the amateurs with the actual observation sites also going to be useful?
Yeah, I would say yes.
Products and so on?
We've done some. There have been a number of exploratory studies looking at the use of WOW data particularly for mapping of weather events as they pass through, and they're proving particularly useful for that. So yes, I would say there's definitely scope for doing so, and it's a case of setting up the process for how. We've done some initial studies, not for rainfall actually, but for the temperature metrics to explore how to do that, because there are several ways that we might think about using these in the context of a sort of a gridding approach like this. Yeah, I would say there's definitely value in this, and linking back to the historical era, we recognise that say in the late 19th century, we are very much reliant on what was an amateur observing network at that time. So it is slightly contradictory of us to be sort of picky for the now and more relaxed about things for the historical observations. So yes, there's certainly a lot of potential there for using all of that.
I can see it, and I can see some variables being a lot easier on the amateur sites than others, and rain and wind probably be pretty difficult because the exposures and so on of sites which probably aren't perfect for amateurs in a lot of cases, whereas temperatures are probably a little less problematic in such circumstances.
But there can still be value in differentiating wet and dry.
Absolutely.
Yeah.
Oh no, absolutely, and there'll be. Yeah. Right, so we'll change tack in the last couple of questions, so to more in the climate change ones, which I thought, sure, since that's where you ended your last section, we should have the last section of the questions. So this one came from Chris. Is the projected increase in extreme rainfall days in future climate simulations mostly down to the idea that we have a warmer atmosphere, so more water that just holds more water vapor, or suggesting more widespread storm type events?
So
or both?
Of those two factors, the warmer atmosphere is the least controversial. So that's very much the expected consequence. The warmer atmosphere holding more water vapor leading to higher rainfall and higher rainfall extremes. So that's pretty uncontroversial and has been a strong message of climate projections for decades now. So that's very clear. The impact on the storminess is somewhat more uncertain because there are a multitude of factors that could influence the response of the large-scale dynamic situation. So that's an area of ongoing research. I mean, there have been some studies that have sort of indicated some potential for increasing the propensity for westerly events during our sort of autumn winter season, but yeah, that's an area of ongoing research on storminess.
Okay, excellent. So thank you, Mark. I'm going to start drawing the session to a close. I've got a final question from Jonathan that's not really directly related to your talk, so I think I'll leave it. I'll do the final sort of wrap up. So firstly, thank you, Mark. This is difficult but I can do a single-handed clap. Thank you. And hopefully you're getting virtual claps through the chat now. So I'll just go through the quick last couple. Remember to keep in touch with the Society, follow the social media and so on, and through the website. And then just some upcoming more MetSoc talks. We also have Ben Pickering in the southeast area for the first Tuesday of May. So get yourselves prepared for that one, where we get more talk of rain. So we're getting used to rain here in the southeast. It would appear. I will bring the session to an end shortly, but let's finally go to answer Jonathan's question, which isn't to Mark really, I think so much as to everyone really. So answer in the chat. I'll leave the session running for a few minutes so that you can answer this one, and I'll leave this up in the meantime. So aside from the endless British rain and from any general meteorological interest, are there any comments on the Arctic wind that's been pouring sleet and snow over the UK today? I've noticed while Mark has been talking, just out of my window just over there, I've spotted at least 2 further snow showers that have occurred, and I'm increasingly glad I covered my little outdoor greenhouse and seeds with fleece for the last few days. So any comments on that? And on that note, I'll just leave it now into the text chat for everybody to answer. I think
so.
it's the best way for this to go.
Earlier today at based on the UK mean max temperature of yesterday. So temperatures at or below that. So that came out of 5.6 as a UK average max for yesterday. So for 61 to 90, that would have been a sort of once every other year type of event. For 91 to 2020, that's a 1 in 10 year event. So it's a sort of, I think, something that used to be normal, but is now unusual. We're sort of less used to because it is significantly rarer than it used to be.
And I saw something that I'm going to consider very rare, in that I went for a little walk earlier around the university campus, and I saw a group of about 15 people playing cricket in snow, which was a thoroughly excellent thing to see. We've got some stats coming up in the chat, but as I said, I think I better leave it for the chat to go, and when things calm down a little in the chat, I'll push the end session button. So thank you again, Mark, for an excellent talk. Fascinating. So I may get in touch with you because I've got my own question that I want to ask you on a personal note.
Thank you.
Thank you.